All right, so this is my third try at doing a physics teacher solution reaction video. So this one I did a Google search for HW3 solution physics, and here's what I found. Something that looks like from about a year ago. So let's give it a shot. I think that I'll do regular speed this time.
All right, so moving on to the next one, it's yet another acceleration problem. So we have our acceleration formula, Vf minus Vi over t. And we're going to think about the things that we know. So I know that my initial velocity here is.
So right away, really great. Right to the formula that he needs. And I think that, they're doing sort of constant acceleration problems. And so when you're doing constant acceleration, this is a super awesome way to go. And, right away putting in the variables rather than, dumping in the numbers right away is going to help them understand what to do. And I think that it's kind of cool that he's using multiple colors. We'll see if there's some sort of color coordination going on.
60 kilometers per hour. We want to go ahead and convert that into meters per second. So we're going to say that 1 hour is 3,600 seconds. Okay, gets rid of hours. And then we're going to go from kilometers to meters. So we're going to say 1 kilometer is 10 to the third, or 1,000 meters. That gets rid of kilometers.
Awesome. I love how he's using the phrase gets rid of, right? So we're given something in sort of daily life, and then we're about to get something in meters per second, because of course, the units that they're given for the acceleration is going to be in meters per second. It's so interesting how, as physics professors, we're always like, oh, get it to meters and kilograms and seconds. And, you could always do this problem in kilometers per hour if you wanted to, but then you'd have to just switch this guy up. And if you switch this guy up to be kilometers per hour squared, boy, I wonder what that would be in kilometers per hour squared, right? So you're going to get these monster numbers because you'd have 3,600 in there twice because of the square. So, it's usually easiest to get it down to meters per second, but I will say that every once in a while, leaving things in the units that people are used to, 60 kilometers per hour, this person sounds like an American accent, so really miles per hour is really what the students are going to be more used to. But if you put in miles per hour, you just got to do more work here, and not everything do people have memorized. 1609 meters per mile is something that is just jammed into my head. I also think it's really interesting that this is a multiple choice, and so I'm curious to see how far he has to go to narrow it down. These are all pretty close to each other, but I wonder how soon this one will be either X'd out or the obvious choice. I mean, I don't know what the answer is yet, but I'm curious to see how it goes.
And now we have a velocity in meters per second. So we end up with 16.67 meters per second.
Okay.
And we're going to do the same thing for our final velocity here, 90 kilometers per hour. We're going to convert that. So
I'm just doing some math in my head. That's so interesting. 16.67 meters per second. So is that fast? Let's see if someone could run. I know that the world record is 100 meters in 10 seconds. So 10 meters per second on average, roughly. So this is 2/3 faster than a human. The fastest human can run. Does that sound like 60 kilometers per hour? Yeah, that sounds about good. Okay. And so now working on the same thing with the 90 kilometers per hour. So it's interesting, right? Because there's two ways to do this one. So you can do the same exact work, and that's super awesome to support your students. Like, look, guys, this will always work, right? So this mechanism of getting rid of the units that you don't like and putting in the units you do like definitely works. But it's also interesting to realize, okay, well, 60 to 90 is 50% bigger. So I'm expecting the answer to be 50% bigger than this. So about, 25 meters per second or something like that.
we get a final velocity here of 25 meters per second.
Nailed it.
The other thing that we know is we also know that our acceleration is 2 meters per second squared. So I'm going to go ahead
and that one, of course, you can leave alone because it's already in meters per second
2
squared.
is equal to my final 25 minus my initial 16.67 all over my time. So 2 is going to be equal to 8.
So it's interesting, right? So this one has stuck out at me to be a little bit more specific. I know it technically has the same number of significant figures, and you guys know that I hate significant figures, but if you ever want to know why, I don't know, put a comment down below or something, and I'll talk your ear off about why. But, already I'm like, well, this seems like it's going to be a wonky number. So it's really basically going to be, 8, it's going to be this 4.2. Right, but I'm curious at what point, if you're a student and you're trying to march through this, at what point would you say, oh, it's obviously not any of these, right? So, to go from 16 to 25, and you're every second, you're going 2 meters per second faster, right? Because the meters per second squared is 2 meters per second per second. So you're going 2 meters per second faster every second. So to go from 17 to 25 is going to take about about 4 seconds. So right away, we're starting to get a clue that these are all way too big. But showing all your work and making sure it all works out is of course what you're, as an instructor, if you're looking at student solutions, that's really what you're hoping to see.
3 over t, and I can go ahead then and solve for t. So I end up getting a time here of 4.17 seconds, which would round, if we're doing 2 sig figs, to 4.2 seconds.
Awesome.
All right, for this next one,
we have another one. Let's do one more.
Track. So the track consists of 2 parallel lines that are each 96 meters long. Okay, and they're connected by semicircles on the curves, each one with their.
So, this is a really interesting way to describe a track, and I think it's right, but it's fascinating, right? So if you're making, I learned this from a mathematician friend of mine. If you're making roads, right, and you think, oh, well, the road needs to go straight, and then it needs to turn. If you actually hook a semicircle directly up to a straight line, so this is what I learned, that you have to immediately accelerate right here. So there's this lateral acceleration. If you're coming along and you have to turn, there's this immediate acceleration you have to do because suddenly you're on a circle. And so it turns out that when they build any sort of curves on highways, they have to smooth this out so that the lateral acceleration goes from 0 to, basically the centripetal acceleration here. So of course we're going to assign problems like this for students because straight lines and semicircles are super easy to do. But as I look here at the question, so really you just need to know the whole lap length. Definitely asking students to be able to figure out all of these lengths and, basically half a circumference is great to test. But I just really am curious to see how much of a difference this is compared to an actual track. I actually don't know if tracks are straight and then immediately connected to a perfect semicircle or not. So anyways, that's really interesting. Let's see where we go here.
Radius of 49 meters. So something like this.
And he's almost drawn this to scale. That's cool.
Completes 1 lap, so starting here, running all the way around.
I love the colors. Awesome.
Seconds, and we want to know the average velocity of that runner. Okay. Well, all we have to really think about is what is our displacement. We start here, we end here.
So let's see, 100 seconds. 100 seconds. Okay, so all I can remember is the mile record is under 4 minutes, and a mile is roughly 4 times around the track, so roughly a minute is the record. I don't know what the 400-meter record is, but I seem to recall back with Michael Johnson days, shows you how old I am, 1996 Olympics, I think it's basically 1 second per 10 meters all the way up to the 400 meters, so 40 meters, something, so 40 seconds is roughly the record for this, and of course we don't know yet if this is going to turn out to be 400 meters, but it sure looks like a track. It sure seems like it's built to come out to be like a track, a formal track. So if it ends up being in the vicinity of 400 meters, then 100 seconds is fast, but not world record fast.
Our displacement is 0 because we are 0 meters from where we started.
Ooh.
Therefore, our average speed is average velocity is also 0. Average speed, on the other hand, would be different.
I didn't catch that.
The distance. We'd actually
have Here I am, totally kidding. Ooh, this is so exciting. And I was getting into the gigantic calculation and everything. And sure enough, it says average velocity And that's a vector component, but you start and you end at the same place. So gotcha. Oh my gosh, I totally got sucked in here. So I wonder if he's going to do the speed calculation. This is a really interesting question, right? So if you're providing this to students, I mean, I say gotcha, not in a negative sense, but like, hey, are you really thinking about this? It's throwing a whole bunch of curveballs at you. Here's some numbers. You got to draw some pictures. You got to do semicircles. You have to figure out the circumference of circles and all of that stuff. When it's so great that you have this, oh, well, hang on a second, average velocity, you start and end at the same place. Easy, right? And so all my questions about, a perfectly curved track, all of that stuff is, maybe not necessary. But the interesting question is it worth it if you're going to post a solution? Well, for those of you wondering about the speed, here you go. I don't know. I think if you're driving home the average velocity concept, this is that perfect moment. Like, hey guys, you worked too hard. Imagine a student who did speed, right? You worked too hard. You did way more work than you needed to. But the question is, do those students really want to see if the work that they did, even though it was the wrong thing, is correct? And so I'm just curious. I mean, I don't know how this teacher does this. Let's take a look, see how it wraps up.
To go through and solve for that. But luckily, we don't have to do that here. We just need to know that our displacement is 0.
All right, so I'm going to stop there. Let's see, can I back it up? Yeah. So I think that this is such an interesting problem because it just sucks you in. You heard all the stuff that I was doing, right? Ooh, 100 seconds. I was doing all of this stuff because I had speed in my head. And when I saw the gotcha moment, I laughed, right? Like, I'm like, oh, that's so awesome. But it's a really interesting question about students. And so I think that students, if they were to do this problem wrong, we want them to learn that lesson. Like, hey, just read the problem, take a breath, read the whole problem, think about what's being asked. Because honestly, I didn't read the whole problem. I was like, oh, let's start drawing some lines. Oh, and he started drawing some lines. I'm like, okay, awesome. And of course, this idea that students should draw a picture first, Ray, so always start by drawing a picture, is a really great idea. And of course, you need the picture to totally demonstrate that the displacement is 0. Hey, you start and end at the same place. I suppose you could just say it. And it's a really interesting question. How would you grade this if a student just checked 0 and showed no work, right? Nothing. And again, of course, I'm going to harp on this, right? That having the students do a video and just say that sentence out loud, like, oh, it's just average velocity, 0. Would be useful. So I'd love to hear if anyone has any thoughts about that. Have a great day, everybody. And hey, physics teachers are awesome.